Today we're going to look at how to find delta H, which we now know is enthalpy, using something called Hess's law. We already reviewed how to calculate delta H using what are called bond enthalpies. We know that in that we're going to look at the bond energies of the bonds broken and the bonds that are then formed in the reaction. In this method, we're using the fact that it doesn't really matter what pathway a reaction takes to get from reactants to products, the change in energy should be the same. So that is what we're going to look at in Hess's law. And remember, last video we looked at using a calorimeter, and that's when we see how much heat, Q, is released through the process, and then we use Q to calculate delta H. So today we're talking Hess's law. All right, what is Hess's law? In the blue, you see the definition for Hess's law. And Hess's law says if a reaction is carried out in a series of steps, the overall change in the enthalpy will equal the sum of the enthalpy changes for those steps. And we'll look at some images that kind of display this idea. Stated in a different way, the overall enthalpy change will be the same if the reaction is carried out in one step or in several steps. So I'm going to pull up some images here. Will kind of give us the idea. So save these on my Pinterest here. This is the first one, and probably one that demonstrates Hess's law the best. So up here at the top, you have your reactants, your oxygen and your sulfur, and you're trying to get to this sulfur trioxide molecule in the products. So this is showing really several ways that we could get there. So one way that we could get there is just by going straight from the single atoms to the molecule that we're looking for. So we can take that one step, and that one step has an enthalpy change of negative 1,420. So it's exothermic, it releases that much energy. The second option would be to take these two atoms, and really you're going to need two oxygens, of course, but we can make SO2 and then use another oxygen to make SO3. So that would be two steps, and there are two delta H values, one for each of those steps. And so the first step releases this much energy, and then this much energy is released. But if you put those together, you get this same exact value that we got doing only one step. We could also tackle this in three steps. So we could put two of the atoms together to make SO, then add another oxygen to make SO2, and add a third oxygen to make SO3. And you see each of those has a delta H value, but when you add them together, you get the same delta H value as you would completing the reaction in one step. Now, how a reaction occurs is not always up to us, but the point is we really don't even need to know how it occurred, because no matter which pathway it takes, it's going to end up with the same delta H value. Let's see if we can look at a few more images here. Take that writing off. This is another one. Kind of displays the same thing. Right, in this one you have at the top sodium ion and just a chlorine atom, and then you're trying to get down to sodium chloride, and again it has some different pathways that you can take, but it's showing that the overall enthalpy change will be the same regardless of whether you go on the path on the left or on the path on the right. Let's see if we can find another one. This one's good because it includes some values here that we can kind of make sense of. So in this one, you have some chemicals over here on the left that we could say would be our reactants, and then we're going to form these products. and that has a value of 90.1 kilojoules, and that's a positive enthalpy change. Or we have these in the center, and then they can go either way. So let's say we wanted to go from what we have here on the left to what we have on the right, but we wanted to use a different pathway. Well, first we would go down here, and that's the opposite of what we see right there, which is negative. So we'd have to make that positive because we're going in the opposite direction. We're actually making this stuff at the bottom instead of using it as reactants. And then we would go up here, and so that would be this delta H value. So if we put those two together, what do you think you get? Well, of course, you get 90.1 kilojoules. So completing this in one step, or reversing this process and then making the products in that direction, we'll get the same delta H value. So no matter the pathway you take, your delta H, your enthalpy change, will be the same. And so that is the point of Hess's law. Now, how do we apply that in practice is what we want to look at. So going back to our slideshow, we'll see some example problems of how this works. So in a Hess's law problem, they will always give you a reaction, and they want you to find the delta H value for that reaction, and then they will give you several other reactions and their delta H value. So that's kind of your clue that this is a Hess's law problem. You'll have a goal reaction like we see up here at the top that we're trying to find the delta H value for, and then we'll have a set of reactions that we know the delta H value for. What we're trying to do is we're trying to put these reactions at the bottom together to form this reaction at the top. So somehow these two reactions at the bottom, reaction 1 and reaction 2, are going to be steps to getting to our goal reaction at the top. All right, so let's see how we work through this. The first thing we need to do is to take that first reaction that we saw and we need to multiply it by 2. So if we look up at the example that we were given, we've got to take these two reactions and form this one. Well, in this first reaction there's N2O5, but in our goal reaction it has a coefficient of 2. And we see oxygen in this first reaction, and it's in the goal as well, but we have oxygen in our second as well. So they're going to go together to make this O2 that's in our goal reaction. It's kind of like putting a puzzle together. And then we have NO2 in our goal reaction, but it's not in this first reaction. So that means it's got to cancel somehow. But one thing I know for sure is this N2O5 can only come from reaction 1. And in reaction 1, it has a coefficient of 1, and in my goal, it has a coefficient of 2. So I know I'm going to be multiplying this by 2. You can kind of see how we're starting to put pieces together. In reaction 2, I want to look for something that's in reaction 2 that's in my goal reaction. And if it's only in reaction 2, it'll make it a lot easier. So NO is not in my goal reaction at all, so I have to try to get it to cancel. And then O2 is in my goal reaction, but it's also up here in reaction 1. That's kind of annoying. Let me see if I can check on something else. This NO2 is in my goal reaction, and it's only in this one, so I can kind of focus in on that. In this reaction, reaction 2, NO2 is a product, but in my goal, it's a reactant. So I know I've got to flip this process around. And when I flip a process around, I change the sign on my delta H. So I know I've got to change the sign on that delta H. And then notice the coefficient. It's currently a 2, and I want to make it a 4. So I know I need to multiply this by 2. So the first one gets multiplied by 2 because that coefficient on N2O5 is all wrong. And this one gets multiplied by 2 to make the coefficient on NO2 correct for my goal. Now what about the oxygen in my goal reaction? Where is that coming from? And does it have the right coefficient? Well, let's put these two reactions together based on what we said needed to happen so far and see what happens. So we're going to move on to the next few slides to do that. Okay, so we took that first reaction and multiplied it by 2. You can see here the coefficients have changed. That oxygen had a coefficient of 3/2, and now it has a coefficient of 3. And the N2O5 with a 2, and the NO with a 4. The second one, we said we were going to flip and multiply by 2. And you can see that's been done here. So they flipped it over and multiplied all the coefficients by 2 and did the same thing to the delta H values. Now we're going to put them together. You can see that you have 4 NOs on the product and the reactant side. So the NOs completely cancel. For the oxygen, you have 3 on the reactant side and 2 on the product side. So 2 of them cancel, leaving us with only 1 oxygen. So when we put that together now, that is exactly like our goal reaction. And to find the delta H value, we simply add up the delta H values after we make the changes that we said. Multiplying the first one by 2, changing the sign on the second one since we flipped it, and multiplying it by 2 as well. So it turns out that the delta H value for this reaction is negative 219 kilojoules per mole. And that means that 219 kilojoules of energy will be released for every mole of this reaction that takes place. Okay, here's another example that we want to calculate the delta H value for. And they've given us 3 reactions this time instead of 2. So these 3 reactions at the bottom have to somehow go together to make the goal reaction at the top. The strategy here is to find something in the reaction at the bottom that's in your goal reaction. And if you can find something that's only in reaction 1, for example, then you can focus in on that. For example, in reaction 1, there's no oxygen or water in my goal reaction, so I don't want to focus on those. Instead, I want to focus on this hydrogen. And I'm going to quickly glance at reaction 2 and 3 and see that they don't have any hydrogen in them. So they're not going to contribute to this hydrogen that's in my goal reaction. Only reaction 1 will do that. So in reaction 1, is the hydrogen on the correct side? It is, so I know I don't have to flip reaction 1. But what about the coefficient? It's a 2 and it needs to be a 4. So I know I'm multiplying this one by 2. Right? In reaction 2, what is in reaction 2 that's in my goal? There's no water in my goal. There's no carbon dioxide. There's no oxygen. So I need to focus on this C3H8 molecule. Is it on the correct side? No, it's not. So I know I have to flip this. So this is going to turn out to be a positive 2,220. Does it have the correct coefficient? It does. So I'm not multiplying. Right? Moving on to reaction 3. There's no carbon dioxide or oxygen in my goal. There's only this carbon. Is it on the correct side? Yes. Does it have the correct coefficient? No. It's currently a 1 and it needs to be a 3. So I know I need to multiply this by 3. Alright, so that is just kind of a first glance calculations. We're going to now do what we said we needed to do to each of those reactions and make sure that it turns out to look like our goal, and then we'll do the math of putting the numbers together. So the first reaction we multiply by 2. The second reaction we flipped, and the third reaction we multiplied by 3. So you can see all those coefficients have now been updated, and the second one has been turned around. Now let's see if there is anything that is the same on both sides that can cancel. Here are 4 hydrogens. I don't see any more hydrogens. 2 oxygens, 5 oxygens, 3 oxygens. The 2 and the 3 are on the same side, so they would add up to 5, and then there's 5 on the opposite side, so all of those can cancel. 4 waters here and 4 waters here on the product and the reactant in reactions 1 and 2, so those can cancel. 3 carbon dioxides, 3 carbon dioxides, so those can cancel. So that leaves me with the 4 hydrogen and the 3 carbon as reactants, and the C3H8 as a product. So put all that together, and we get, sorry, I went backwards. we put all that together, we get exactly what our goal reaction was, and then we put the values together after doing the math, and we get negative 103.8 kilojoules, and again, that's kilojoules per mole. This program does not write the per mole very regularly, but you need to ensure that you do, okay? Because these delta H values are critically per mole. Alright, the last way that we can calculate delta H is something called enthalpies of formation. What is an enthalpy of formation? The definition is in blue. It is a hypothetical value that indicates how much heat would be lost or gained during the formation of 1 mole of that compound from in its most common form from its elements in their standard state. So what this is saying is, if I wanted to make that compound using its elements that are commonly found on Earth, how could I put those together and what heat would be either lost or gained? Enthalpy of formation is shown with a delta H and a tiny f to show that we're talking about the heat of formation, and then the circle at the top tells you that we're talking about if it is standard. So if it's at 25 degrees Celsius and 1 atmosphere, standard state. The enthalpy of formation comes with a special type of equation, and you'll often be asked to write these or identify these on the AP exam. So for a standard enthalpy of formation, we always write it so that there is 1 mole of product. So for example, if we are doing the standard enthalpy of formation for methanol, I would start by writing methanol as my product, and it's always 1 of those. Never change the coefficient in front of your product when you're doing an enthalpy of formation, because it's for 1 mole of your product. From there, you want to add reactants to be all the elements in the compound. So when I say element, remember that's a single type of atom. So our elements are carbon, hydrogen, and oxygen. So carbon plus hydrogen plus oxygen will make methanol. Your carbon, hydrogen, and oxygen must be in their standard states. So the standard state for carbon is a solid. The standard state for hydrogen is H2 gas because it's a diatomic molecule. And the standard state for oxygen is also O2 gas. Once you have your elements placed in, you then balance using the correct coefficients. But you may need fractions because you cannot change the coefficient on your product. It has to be a 1. So we have carbon, there's only 1 in the product. Hydrogen, there's 4, so that's 2 H2s. And oxygen, there's only 1 in the product, so we need half a mole of O2 gas. Now, typically we don't see fractions in reactions because we don't think about using half an atom or half a molecule. But if you're thinking about moles, you can use half a mole of something. So these types of reactions, this enthalpy of formation, is one of the only times we'll see these fractions, because we want to say that we're forming 1 mole of product. Because our delta H value, which you see there, is negative 201 kilojoules per mole, that means that if you make 1 mole of methanol, then you're going to release 201 kilojoules of energy. Anything that's already in its standard form has an enthalpy of formation of 0. For example, calcium is standardly a solid, right? God made it that way. It's already on the earth. It doesn't take any energy to form calcium solid. It just is. So these things have heat of formation values of 0. You'll see there oxygen gas, O2, has a heat of formation value of 0. But if you wanted O3, or even just a single oxygen atom, that would take heat to produce because that's not its standard state. So heat of formation values are 0 for things in their standard state. So how do we use these HF values to find the enthalpy change for a reaction? Well, this is the equation. We're going to take the HF values of the products and add those together, and subtract the HF values of the reactants, and that will give us the delta H value for the entire reaction. We need to keep in mind that we have to use our coefficients when we use this equation. Now this becomes confusing to people because remember when we were doing bond enthalpy, it was bonds broken minus bonds formed. And the bonds broken are in the reactants, right? So when we have bond energy, we were doing reactants minus products. If we have heat of formation values, we're doing products minus reactants. And the reason is because the products are formed and we're using formation values. The reactants are not being formed, so we have to change the sign by subtracting our reactants. Alright, here's an example. They give you a reaction at the top and they want you to find the delta H of the reaction. So they take the heat of formation values for iron and aluminum oxide, and then iron oxide and aluminum for the reactants. So you have 2 times the iron value. Okay, I'm looking down here. This last one. 2 times the iron value, which is 0 because it's in its standard state, which is a solid. And 1 times the aluminum oxide value. Now this value just came from a table. This table is in the back of your book where you can easily Google enthalpy of formation values and you'll get the value for every molecule imaginable. So those are our products minus 2 times 0 for aluminum solid because that's its standard state, and 1 times the value for iron oxide. Once they did the math, they came out with this negative 854.3 kilojoules per mole. So that means that much energy is released, exothermic because of the negative sign, each time 1 mole of that iron oxide reacts with 2 moles of aluminum. That is our enthalpy value for the entire reaction. Right, this is another example that you could try. At least set up, think about what would be our products minus reactants and what, if anything, would have a 0 value. To calculate, you would need to look up those values for the heat of formation for the molecules in a table. Here are some sample enthalpy of formation values for different compounds. I want us to pay particular attention to the reactions. On the product side, we always have 1 mole of the product. And then on the reactant side, we have the reactants as elements in their standard state. So we have gold and then oxygen gas, silver, oxygen gas, copper, oxygen gas, etc. And then you'll see how much heat is released or required when these form. So for gold oxide, it requires heat to make that. So you would have to heat up the gold, for example, to make that. Then for silver, it releases a little bit of heat when that's made. Copper releases a little more. Lead, a little more. Tin, this releases a lot of heat when that is oxidized. And then iron releases a lot of heat when that is oxidized. What this is telling us is that in order for gold to oxidize, that's another word for rusting, you actually have to put energy in to make that happen. But these other metals, they rust easily and then even more easily as we go down, and we know that iron rusts really easily, which is why it has such a negative delta H value. It is preferable. It releases heat. So that's why gold is so used in jewelry, for example, because in order to tarnish gold, you actually have to attempt to do that. It doesn't happen naturally. But in order to tarnish iron, like an iron nail, that's a process that happens what we call spontaneously or favorably in nature. All right, in example 3, they want us to use the enthalpy of formation values that they're giving us to determine the delta H reaction for a reaction between carbon and iron 2 oxide to produce iron? Well, first off, we need to know what the reaction is that we're looking for. So let's see if we can write out the appropriate reaction. This at the bottom is the reaction we're trying to get to. So we're reacting iron oxide with carbon, and that's going to be a single replacement reaction to produce iron and then, of course, carbon dioxide. So how can we find the delta H value for this reaction? Well, one way is using Hess's law, which you see that they did here. So they took the first reaction and they flipped it to make iron oxide a reactant, and they multiplied it by 2. And so they did the same thing to their delta H value. And then they took their second reaction, which had carbon as the reactant, and they just multiplied it by 3 because it was already in the correct reactant to product method. So once they multiplied it by 3, they then put them together and they found this delta H value. But there's another way to solve this. So you could treat it like a Hess's law because you have the reactions given, or you could treat it like a heat of formation because that is what values you have here. So you have the heat of formation for iron oxide and the heat of formation for carbon dioxide. If you have heat of formation values, you can do products minus reactions. So we have our product, carbon dioxide, with a coefficient of 3. So we multiply that by 3. Now this iron is in its standard state, so we don't need its HF value. It would just be 0. So products minus reactants. For our carbon, that's in its standard state, so it would be 0. And then we would just need to take this Fe2O3 value and multiply it by 2. So it would be the carbon dioxide times 3 minus the iron oxide times 2. And you'll see if you look at the Hess's law example, that's exactly what they did. The carbon dioxide got multiplied by 3 minus the iron oxide value times 2. So whichever way you approach that problem, you will get the same answer. Alright, one more quick thing before we leave this lesson. These delta H values or enthalpy values are directly related to stoichiometry. So I've been saying this whole time, it's per mole, it's per mole, it's per mole. So when you see a delta H value, it may or may not have per mole written. But you always want to think of it in your head, per mole. We haven't been really specific so far about what that per mole meant. Okay, I tried to explain that a little bit earlier, but maybe it wasn't too clear. The per mole is per mole of everything in this reaction with its coefficient. So when it says per mole, it's saying per mole of the whole reaction, but they have different coefficients. So if you're talking about the peroxide, which we are in this problem, then it's per 2 moles of hydrogen peroxide. If you were talking about oxygen, it would be per 1 mole, because that's its coefficient. Or for water, per 2 moles, because that's also its coefficient. That allows us to create conversion factors. In this problem, the question is how much heat is released when 3.56 grams of hydrogen peroxide decompose. So we start out with the 3.56 grams. Now, as always, whenever we're working problems, if we have grams, we likely change them into moles. So that's what we did in this first step. And once we have moles, we can use our delta H value, kilojoules per mole. The coefficient here depends on what your moles are. We're dealing with moles of hydrogen peroxide right now, so it's per 2 moles of hydrogen peroxide from the balanced equation. And then you do the math and you find that that releases, that's when we have a negative, 9.73 kilojoules of energy. It's no longer per mole, this is now a Q value, because this is for a specific amount of our reactant. So the delta H value is for the whole reaction, but if we have a specific amount of something that we're concerned with, then we'll do the calculation, turn this into a conversion factor, and we'll find a Q value. All right, that's it for now. We'll jump back in on Thermo 3 after reviewing some and doing some more practice problems together.